Assalamualaikum and good day. Welcome to CMA422. In our last video, we have learned about what consists in reinforced concrete. One of it is the concrete, and we learned about the concrete properties. In this video, we're going to learn on the reinforcement. Reinforcing bars are produced in two grades, which are hot roll mild steel bars that have yield strength, which is Fy of 250 Newton over mm square, and another one, hot roll or cold work high yield steel bar that have yield strength of 460 Newton over mm square. Steel fabric is made from cold drawn steel wires welded to form a mesh. It has a high yield strength, which is 460. Okay, right now you have two types of bar, which one is mild steel. Mild steel will look like this. If you ever went to any construction site before, you will see this type of bar. And for hot roll or cold work high yield steel, this is the one macam ini ataupun like this. Normally inside you akan nampak this one. And it's also state that Fy ini adalah simbol untuk yield strength ataupun tensile strength 250. This one for mild steel. You have to memorize this Memang kita akan sentiasa pakai And another one is high tensile ataupun kita panggil dia high yield It is Fy equal to 460. The stress strain curve for reinforcing bars are shown in figure. So this is the one. Hot roll bars have definite yield points. A defined proof stress is recorded for two cold work bars. So if let's say dia buat tensile test, dia akan dapat this kind of result. The value of Young modulus of elasticity is 200 kN per mm square. The behavior in the tension and compression is taken to be the same. Mass T-bar are produced as smooth round bars like this one. High tensile steel or bars are produced as deformed bars in two types defined in the code to increase bond stress. The first type is square twisted cold work bar. This type is obsolete, and the other one is hot roll bars with transverse ribs. So this one is obsolete, and this is the one yang ini type 2 and this is type 1. Tak pakai dah. Basis of design. The design of reinforced concrete elements to British standard BS 8110 is based on limit state method. BS ni adalah British standard, which is a standards lah, macam MS adalah Malaysia standard, and this one for British lah, dia ada standard The criterion for safe design is the structure should not become unfit for use. For example, that it should not reach a limit state during its design life. This is achieved in particular by designing the structure to ensure that it does not reach. The first one, we have the ultimate limit state, which is ULS. So ultimate limit state enables the designer to calculate the strength of the structure. The ultimate limit state it is the whole structure or its element should not collapse, overturn or buckle when subjected to design load. And for the serviceability limit state, the structure should not become unfit for use due to excessive deflection, cracking or vibration. Usually for serviceability limit states, this one dia lebih kepada appearance which is kalau kita tengok on the cracking, on the deflection, dia lebih kepada appearance of the reinforced concrete elements. But for the ULS, which is the ultimate limit state, this is more critical because of kita tak nak the building fail. Okay, because of kita nak avoid collapse, kita nak avoid overturn, kita nak avoid buckling. So that kita make sure that the structure that we design does not reach all these limit. So limit ni adalah paling maksimum. Okay, some of the ultimate limit state to be considered are for ULS, it is bending, shear, direct compression or tension and overturning. And for SLS, it is deflection, cracking and vibration. When designing a particular concrete element, it is usual to first ensure that the ULS is not exceeded and then to check that the relevant SLS are also satisfied. So first, we're going to check on the ULS, then later then we're going to check on the SLS. Having identified the relevant limit states, the design process simply involves basing the design on the most critical one and then checking for the remaining limit state. This requires an understanding on one, which is the material properties. So in dalam British Standard, kita akan refer pada clause ni, clause 3.1.7 and loading clause 2.4.1. Now we look at the reinforced concrete beam design. Types of beam section. Three common types of reinforced concrete beam section are: the first one is rectangular section with tension steel only. This is the first one. This is the cross section view. Maksudnya you potong reinforced concrete beam tu, you will get this kind of view. This generally occurs when designing a given width of slab as a beam. And B, it is rectangular section with tension and compression steel. If you look at above here, this is what we call as compression steel. And this is tension steel. Ini dia ada tension steel sahaja. Flange section or either T or L shape with tension steel and with or without compression steel. This is flange type of, maksudnya T lah ataupun L . Okay. In our syllabus, we just going to learn up until this one, A sahaja. Another two ni kita tak belajar. The design macam mana just a simple one which is the rectangular section with tension steel. The characteristic strength of grades of material are as follows. Concrete, the FCU ni adalah compressive strength. You ada nampak untuk steel, FY kita panggil this one adalah tensile strength. For concrete, we call it FCU. It is compressive strength. FCU is 28 days cube strength in Newton per square millimeter. The minimum grade for RC are given in table 3.3. So this is the table 3.3 kalau according to depan ni. These grades C30, C35, C40, C45 and C50 in newtons per square millimeter. For example, if you look at here, the concrete grade is C75. That means that the FCU is 7.5 Newton per mm square. If the concrete grade is C30, the FCU is 30 Newton over millimeter square. And this is the one for the steel reinforcement that I have explained previously, which is, we call this as FY, 250 for mild steel and 460 for high yield steel. This one, as being explained. The characteristic design loads, clause 2.4.1, this is in British standards. The characteristic of service load are the actual loads that the structure is designed to carry. The characteristic loads used in design are defined as follows. First, we have the characteristic dead load. This the one I believe that you are very familiar with the dead load, with the imposed load or live load, and with the wind load. And just notice here the symbol. For dead load, we call it GK. For imposed or live load, we call it QK. And for the wind load, we're going to call it WK. So design load is equal to characteristic load times with partial safety factors for loads. Biasanya engineer dah tahu kalau bangunan tu mungkin 2 tingkat, size dia besar ni, berapa square meter like that, dia dah tahu berapa sebenarnya loading dia. And sebenarnya ada calculation for that. Loading, for example, dari roof, you nak transfer ke beam, berapa berat roof like that. So itu adalah kita panggil as loading, characteristic load dia. And characteristic load ni kita kena darabkan dengan partial safety factor for loads to make sure that kita lebihkan design kita daripada the actual load tu, supaya the elements of reinforced concrete yang kita design tu boleh support lebih lagi daripada actual load. Kalau you tengok dalam table ni ya, we have 1.41, 1.60, blah blah blah. Usually we going to use the first one, which is that and impose and earth and water pressure. Adverse, we going to take adverse as the that load punya partial safety factor. And for imposed load, we going to take as 1.6. It always depends macam mana kita nak ambil this thing, but normally kita akan ambil the first one. All this thing is being extracted from the British standard, bukan saya yang buat Kita akan ambil yang first one for that load 1.4 and for imposed load 1.6. For wind load tak ada. Okay, normally for bangunan, a simple building like 1, 2, 3, 4 tingkat, kita tak akan consider the wind load because the effect of wind is very minimum. The ultimate design load acting on the member will be the summation of the relative characteristic load combination multiplied by their respective partial safety factors. So this is the one yang I explained earlier. This is the partial safety factors. Ini dead load punya, and this one imposed load ataupun live load. After kita kira the ultimate design load using this formula, we're going to calculate the ultimate design moment using the formula of M equal to WL square over 8. About this formula, I have explained to you in our first chapter, which is the timber beam design. But never mind, I will explain again so that you will understand the use of this formula instead of kita draw balik the SFD and BMD to get that maximum value. Kalau you ada loading like this, okay, UDL, you boleh kira dia punya ultimate design moment, maximum bending moment. Bila UDL you like this, obviously you punya shear force akan jadi macam ini. Ni adalah SFD. And the BMD is going to curve like this. Curve And the value here adalah maximum bending moment yang you pernah belajar sebelum ni. And this maximum bending moment adalah sama dengan ultimate design moment. Value ni you can simply dapat daripada calculation pakai this formula, which you don't actually need to draw the SFD and BMD, provided that the loading on top of the beam here adalah UDL dan dia sama for the sepanjang-panjang, for example 10 meter length of the beam, dan the UDL dia pun sama sepanjang-panjang tu juga 10 kN per meter, dan you boleh pakai this formula. After we calculate the maximum bending moment, we're going to calculate the design ultimate moment resistance, or we call it as MU. Formula for MU is 0.156 FCU PD square. This is the cross section of the beam. Ni adalah B. Okay. D tu is actually daripada, for example, you have 2 steel bar. D is actually daripada top of the beam up until the center of the steel bar. That's what we call as effective depth. Berbeza dengan depth. Okay, total height ataupun depth, call it as H. Okay, tapi effective depth dia sampai center of the steel bar. That is effective depth. Okay, beza dengan H Okay, we must make sure that the MU must be bigger or equal to M, which means that it is a singly reinforced concrete beam. So MU ni sebenarnya adalah maximum. Okay, sebab nama dia pun design ultimate moment resistant. Kalau you dapat M, because M ni, the one yang you kira ultimate design moment ni, ini adalah daripada berat loading tu. Okay, berat loading tu you dapat, you kira, you dapatlah value moment dia berapa daripada berat loading daripada berat slab ni. For example, transfer pada beam. Itu adalah dia punya moment. But here, the ultimate moment resistance adalah moment yang paling tinggi yang boleh beam size macam ni, okay, size yang ikut B dia banyak ni, D dia banyak ni, boleh resist sebanyak tu. Okay, jadi you must make sure that ultimate moment resistance ni untuk beam yang size macam ni takkan kurang daripada moment yang disebabkan oleh loading. Okay, so sebab moment kalau disebabkan oleh loading lebih besar daripada moment yang beam tu boleh resist, dan akan jadi masalah kan. Kalau ultimate moment resistance ni lagi besar ataupun sama dengan moment yang disebabkan oleh loading, you boleh design dia as singly reinforced concrete beam. A singly reinforcement will be sufficient to resist the design moment. However, kalau you dapat MU is less than M, meaning loading you lagi besar daripada apa yang dia boleh resist oleh beam untuk size macam ni, kita akan design dia as doubly reinforced concrete beam. However, kita hanya akan belajar up until here. Sampai sini kita tak belajar, so don't worry. Soalan dia takkan jadi up until this one lah. Dia akan sampai sini sahaja. After we dah make sure yang M tu tidak lagi besar daripada MU, meaning dia adalah singly reinforced concrete beam, right? We need to calculate the value of K. So K ni, dia tak ada nama dia adalah K. K is equal to M over FCU PD square. This is the formula. M is design ultimate moment, meaning moment daripada loading tadi, which is the value of M sama dengan WL square over 8 tu. And then FCU, which is the characteristic strength of concrete. FCU berapa? FCU 45, FCU 30, FCU 40. The B, which is the breadth, lebar cross section of the beams. And D is the effective depth, meaning D yang ini berapa. So kita dapat kira value K. K must be less or equal to K prime. K prime ni adalah 0.156. Dia takkan boleh lebih daripada K prime. Kalau dia lebih pada K prime, maksudnya M will be bigger than MU. Kalau K you dapat lebih besar daripada K prime, maksudnya M tu adalah lagi besar daripada MU. Which is bila kita proceed up until this stage, for your syllabus kita takkan dapat this kind. So kita takkan dapat K ni akan lagi besar daripada K prime. Takkan juga. Right, so value dia mesti lagi rendah atau sama dengan K prime. And then Z, which is the lever arm. Lever arm is a perpendicular distance between the line of action of couple forming compressive and tensile force in a section. The magnitude of lever arm changes with the change of section type, which are balanced, under reinforced and over reinforced section. As you know, compressive force is resisted by concrete and tensile force is resisted by reinforcement. Lever arm ni adalah distance daripada line yang antara tensile force dan compressive force. Okay, dia tak sama sebab dia boleh berubah. Kalau katakan balance, Z ni value ni akan lain. Kalau under reinforced, Z value dia akan lain. Kalau over reinforced, Z value dia akan lain. Formula dia is D, which is the effective depth, dalam kurungan 0.5 plus, you have to square root everything, bawah tu 0.25 minus K, okay, and divide with 0.9. Ni minus minus K and divide with 0.9. And you must check it must be less than 0.95D. This one dia ada explain lah. By limiting K prime to 0.156 in BS 8110 implies that the not available depth does not exceed 0.5T and hence that the steel in tension will reach its ultimate stress before the concrete fails in compression to avoid sudden failure. So senang cerita, kalau K awak ni less than K prime, maksudnya takkan fail. Sudden failure. Kalau K lebih daripada K prime, okay, dia akan still in tension, we reach its ultimate stress. Okay, jadi dia akan fails in compression and akan fail lah. And same goes with M is bigger than MU. So definitely you know kalau K bigger than K prime, meaning M awak akan lebih besar daripada MU. So this thing is related. Case. Bending ULS, simply supported rectangular beam are designed so that the concrete above the neutral axis is capable of resisting the induced compression, and tensile reinforcement available capable of resisting the induced tension is introduced below the neutral axis. So there is a reason kenapa dia letak reinforcement dekat bawah, dia bukan letak dekat tengah-tengah. Untuk beam, compression dekat atas ni lebih tinggi daripada tension. Dalam bending stress, kita boleh actually draw macam mana which part of the beam yang in tension and which part is in compression. So normally for beam, bahagian atas akan lebih in tension and bahagian bawah akan lebih in compression. If you going to draw the bending stress diagram, you will get something like this, which is sama tak dengan ini. Okay, ini adalah bending stress. Right, so ke atas ni kan you akan dapat value dia positif and bawah ni negatif, which means it is in compression. And this is tension. And as you know, compressive force ataupun compressive stress is resist by concrete. Okay, jadi concrete dia lebih pada compression and reinforcement lebih kepada tension. So bawah ni adalah area in tension. Bila beam tu you put a lot of load on top of it, maksudnya dia transfer load banyak atas this beam, what will happen, beam you akan start nak bend. Jadi yang bawah ni dia dalam tension and atas ni it is in compression. Pull dia ke dalam, yang kat luar ni dia nak pull out. Okay, dia in tension. So kita akan letak reinforcement dekat bawah ni. After we calculate K, kita dah calculate Z, dan kita kena calculate area of steel. Sebab sekarang kita nak design. So kita kena design daripada segi size of the beam sampai kepada area of the steel. Steel dia banyak mana you nak letak. AS is steel area. M is equal to 0.95 FYZ. M ni you tahu, ini adalah ultimate bending moment. 0.95 tu formula. And then Fy adalah characteristic strength of reinforcement. Maksudnya tensile strength of reinforcement yang you tahu whether it is 250 ataupun 460. And then we have Z, which is the lever arm yang I ada tunjuk dia punya formula. Reinforcement clause. Too large an area reinforcement should also be avoided since it will hinder proper placing adequate compaction of the concrete around the reinforcement. For rectangular beam with overall dimension B and H, the area of tension reinforcement AS should lie within the following limits. So AS, limit dia inilah. So kalau Fy dia 250, ini bukan 500, ini 460. Apa maksud dengan ayat di sini? Okay, maksudnya, for example, you have this kind of beam. Rectangular beam like this. Let's say reinforcement you letak terlampau besar. And then kita kena avoid letak size bar yang terlampau besar dalam beam. You nak pour concrete inside. Obviously dekat side you akan pasang formwork. Okay, formwork. The other side formwork formwork. And then you akan pour concrete from top. If the size of the reinforcement is too big, okay, jadi macam mana all the concrete nasib in nak duduk dekat area bawah ni. Okay, because kita bukannya letak dulu formwork kat bawah and then pour concrete kat bawah, lepas tu baru letak bar, lepas tu baru pasang reinforcement kat tepi ni, tak Kita siapkan dulu formwork and then you letak spacer sikit. Okay, jadi you akan letak concrete. How the concrete going to fill all the void kat bawah-bawah ni semua. Bila you dah kira AS, then you dah dapatlah the area of the steel. The area ni, kita nak tahu berapa banyak steel bar yang you nak pakai. For example, you dapat 1260 mm square. So you're going to look at this value. Ada tak yang 1260? Ada. So kalau ada, you can just pakai 4 for numbers of bar T, which is ini high tensile. Normally for main bar yang kita kira AS ni, ini adalah kita panggil dia as tensile reinforcement sebab dia resist tension. Jadi kita panggil dia tensile reinforcement ataupun main reinforcement ataupun main bar. Ni biasanya main bar ni kita pakai dia T, which is referring to high tensile ataupun high yield steel. 4 numbers and the size is 20. Which means that di beam you, mungkin you akan letak 4 numbers of bar like this. Ada 4 biji, size 20 mm, diameter. Ini sebenarnya refer pada diameter. All this number, the area of the diameter. Kalau you kira ada 4 biji yang size dia 20 mm. Okay. You tahu satu biji size 20 adalah 314. Kalau you check lah, you boleh pakai calculator. Satu biji size dia punya AS dia adalah 314. Kalau 4 biji, sebenarnya AS dia adalah 314 mm square. You darab dengan 4. Lebih kurang lah sebab ni dia ada round up So itu actually dia punya area. Area cross section ni satu biji ni. Kalau you kira area ni berapa, bulatan kan sebab dia adalah reinforcement bar, dia bulat. Okay, area cross section dia adalah 314 untuk satu biji size 20 mm diameter. Okay, ini adalah diameter. So sebenarnya pi d square over 4. You pakai pi darab 20 mm kuasa 2 per 4 adalah sama dengan 314. And actually sama je dengan size 16 ke, size 12 ke. It is actually bar size tu adalah diameter. R miles T bar and Y high yield bar. Okay, ini yang saya cakap tadi. Bars are designated on drawings as, for example, 4T25, i.e. a 425 mm diameter bar of grade 460. This system will be used for specified bars in figure. Maknanya kalau 4 biji number of bar, T ni you tahu dia adalah high tensile and 25 tu adalah bar size ataupun diameter dia. Okay, kalau katakan it is part R 25, meaning this is mild steel. Then we go to the minimum spacing of reinforcement. The limits on the maximum distance between bar arise from the need to ensure that the maximum crack width does not exceed 0.2 mm in order to prevent corrosion of embedded bars. That's why kita kena avoid sangat cracking of concrete sebab ada bar dekat dalam. If let's say it is being exposed to the environment, dia boleh menyebabkan corrosion. This clause states that the following, the horizontal distance between bars should not be less than H aggregate plus 5 mm. HAGG. HAGG ni adalah aggregate size. Maksudnya bila you buat concrete, you akan add aggregate yang paling besar. Part size dia yang paling besar. The gap between the corresponding bar in each row should be vertically in line and the vertical distance between bars should not be less than 2 HAGG divided by 3. Where HAGG is a maximum size of course aggregate. So aggregate yang you mix together untuk hasilkan konkrit tu, aggregate yang paling besar adalah for example katakan 20 mm. So itu adalah HAGG. The clause also states that if the bar size exceed HAGG plus 5 mm, the spacing should not be less than the bar size. Note that the pair of bundles are treated as single bar or of equivalent area. Kalau you nampak between bar ni ada gap. Ni kita panggil dia spacing. Spacing ni mesti HAGG plus 5 tak kurang daripada value ini. For example, the maximum aggregate size is 20 mm. Right? Bila you kira HAGG plus 5 mm adalah 25 mm. If let's say you kira-kira, you design, you buat this one, you dapat 26. Maksudnya okay lah. Since it is bigger than HAGG plus 5 mm. Dia tak boleh less Okay, bus size ni tadi kalau you tengok bus size. Ya, ini dia. Standard dia tak berubah-ubah. Memang 6, 8, 10, 12, 16, 20, 25, 32, 40. Kalau you nak size yang lain daripada yang ni, you kena tempah lah. Okay, custom size. This is factory made and typical size Kalau kata kan, bus size ni 20 mm. Okay, 20 mm dengan 25 ni, 25 lagi besar. So tak ada masalah Kalau bar size you adalah 4 ataupun 32, kita takkan pakai compare dengan HAGG ni. Kita akan comparekan dengan bar size. Maksudnya sekarang ini spacing ni, kalau bar you size 32, spacing ni must be bigger than 32. 32 tu adalah minimum. Sebab bar size ni ayat kat sini. Macam mana kita nak kira spacing? Ini example I bagi. This is the cross section of the beam. Beam you panjang macam ni. Then you potong lah. You akan nampak something like this inside. So you nakkan spacing tengah ni berapa? Sebab kita nak make sure spacing tu cukup. Ini berapa? Okay, ini kita panggil dia B. So B must be minus width. Okay, apa yang you nampak kat sini? You nampak ada 2 biji bar. So 2 bar. 2 kali diameter bar tu lah. Sebab ini berapa you nak tolak ni. Kita nak tolak semua yang kat dalam sebab kita nak dapatkan tengah ni je berapa. Kat sebelah bar ni, ini kita panggil dia as link. Dia adalah bar. Sebab bar macam link ni kan, contohnya you punya main reinforcement dekat bawah ni. And then mungkin you ada hanger bar kat atas. And then you ada reinforcement keliling lain So ini kita panggil dia as link. Dia keliling panjang-panjang macam ni, dah ada banyak. Dia berpusing. Kalau you nak tolak 2 ni sebab dia berpusing kan, minus 2 diameter of link. And then kita mesti ada concrete cover sebab kita nak elak daripada reinforcement tu exposed to the environment. So kena ada concrete lah dekat keliling tu, which is the cover. We call it concrete cover minus 2 concrete cover. Concrete cover kita panggil dia C. Kita akan divide kan dengan number of bar main reinforcement tu minus 1. Sebab kalau you dah tolak ni semua, so minus number of bar 2. So 2 tolak 1. So tinggal 1. Bagi 1. Sebab dia tak ada banyak. Kalau katakan dia macam ni. So you ambil 4 minus 1. So bahagi 3. Sebab space you sekarang ada 3 sahaja. Betul? So you kena bagi sama rata lah 3 space tu. I ada explain kan. Pasal apa beza H and apa beza D. You nak dapatkan total height which is from top until the very bottom of the beam, which means that D, which is the effective depth, plus dengan, sebab effective depth you sampai tengah ni, you ada lagi half bar kat sini, separuh bar, diameter of bar, link. Okay, you ada link lagi, which is kalau diameter untuk link kita panggil dia diameter prime, and then you ada concrete cover kat bawah ni. That's why macam mana you dapat the total height ataupun the overall depth of the beam, it is equal to effective depth plus half of main bar plus dengan diameter of link plus dengan concrete cover. This is the concrete cover yang I mentioned earlier. The code states that in section 3.3.1 that the actual cover should never be less than the nominal cover minus 5 mm. The nominal cover should protect steel against corrosion and fire. Sebab kalau kena fire, steel you akan cair. So that's why we need a very good penebat lah. Okay, penebat dia adalah concrete. The cover to a main bar should not be less than the bar size, or is the case of pairs of bundle and size of single bar of the same cross-sectional area. The cover depends on the exposure condition given in table 3.2 in the code. We have mild, moderate, severe, very severe, most severe and abrasive. It always depends on the weather. Maksudnya kat mana sebenarnya site you, kat mana bangunan tu. For mild, okay, you see this is 25. So normally kita akan pakai 25 mm as the concrete cover. That will be all for the recorded video. We will proceed with the example to show you how to calculate for reinforced concrete beam design. Thank you so much and have a nice day.